All right, so we're going to talk about three types of energy transfers or heat energy transfers. Convection. For convection, it's kind of like a fan that blows. That's the best way to word it. So in a fireplace, heat transfers occurs in all three forms. So convection is like the air, right? So you can have the air blowing. I should probably change that to the color. So what happens is that hot air moves, okay, but it also circulates. All right. So convection is almost always associated with like some sort of fan. And then conduction, which is an interesting one. Conduction is always associated with like contact. They actually all operate the same way, which is funny to me, but conduction is more like contact. And then the other one is radiation. Now, radiation is slower, and it has a tendency to be, they're all technically contact when you think about it, right? It's on a molecular level. That's funny, I can't see the yellow one. We'll have to change that to orange. So that's radiation, okay? But really what's going on is you have molecules interacting with each other, and if one molecule has more kinetic energy, it has more thermal energy, because thermal energy and kinetic energy are measuring kind of the same thing. They're just measuring energy. If something with more thermal energy comes into contact with something that's less thermal, once they come into contact with each other, there's a transfer until they reach an equilibrium. Okay, it depends on how much contact they have. Convection speeds up that process because you have some sort of air circulation. And so because you're circulating the air with a fan, you're causing the air molecules to interact. Conduction, usually you have like a viscous fluid as opposed to air, so there might be some sort of water or oil. Those upright radiator heaters, they have oil in them. You could hear the oil creaking and expanding in them. And then radiation is just natural heat that just kind of radiates from them. Now, they're all based on a transfer of heat from molecule to molecule. So I'm going to go to the next slide. In a house, what we do is we put fiberglass insulation in there, and the insulation isn't very conductive. In other words, the molecules in the insulation doesn't transfer energy that much, and the fiberglass, because of the structure, it just doesn't absorb heat, it doesn't transfer heat, and it's kind of locked in because it's a solid, so it doesn't move as much. Where an air molecule is free to roam, which means if it has thermal energy, it'll bombard other air molecules and transfer that energy, okay? So this is what it looks like kind of on a molecular scale. You have, like let's say if I have a heat vent, which I do in this classroom, where the hot air comes in to the room from our heating system here at the school, and then there's another part of the room that's cold. What happens is, on a molecular level, the colder molecules, they're floating around. The higher temperature molecules have a greater energy, and they will collide into the lower energy, lower temperature. And when it does that, there's a transfer of the heat. There's a transfer of kinetic energy, right? Which also implies or means that there's a transfer of heat energy. Okay, so molecules in two bodies at different temperatures have different average kinetic energies, collisions occurring. at the contact surface tends to transfer energy from a high temperature region to a low temperature region, right? The low temperature area absorbs that energy. In this illustration, a molecule in a low temperature region has a low energy before the collision, and then afterwards it has a high. So what you have is, and I don't know if I can, if you guys want to watch me do this, but I'll try my best to illustrate it. It doesn't want to cooperate today. Well, maybe I'll go back to Google Slides. Okay, so this has high energy, right? And it collides with this one, which has low energy. After they collide right here, this one absorbs some of that heat energy, right, and kinetic energy, and this one gives some off. And it keeps going until they have the same energy or they reach thermal equilibrium, okay? You guys have that written down? All right, so then mathematically we can make a prediction about those relationships. On the next slide here, whoops. On the next slide here, this is what it looks like when you have a solid. So you have a high temperature, temperature 2, and heat is conducted through a solid. In this particular case, the heat conduction occurs through any material represented by the rectangular bar. It doesn't have to be a rectangle, it's just a rectangle showing that you have a high temperature on one end of an object and a low temperature at the other end. Okay. This could be like window glass. They put walrus blubber. I don't know why they use that, but it's kind of funny. And they said that the temperature of the material on the left has a greater energy than the temperature on the right. And so the heat transfer occurs in this particular case from the high temperature to the low temperature. And so this rate of transfer is inversely proportional to the thickness of the object. Okay, and I'm going to give you a formula here in a second. So that relationship is, as soon as I can get my pen to work here, I'm going to try to write it over here on the side. There we go. We need to undo. I can't see it, which is bizarre. Okay, here we go. So we have our heat energy over T, lowercase t for time, is equal to K, which is thermal conductivity, and I'll list these variables in a second. A is this area. We have T2 minus T1 all over the thickness, which is D, the distance between them, okay? And so K is the thermal conductivity. In the textbook, it has a listing of thermal conductivities of various materials. That's supposed to be conductivity. Temperature 1 and temperature 2, A just stands for the area. And you can calculate that area based on the shape. And it's just geometry. We figure out the area. And D is sometimes referred to as thickness or the distance. Okay.
What's the variable for K? What are units is each that variable?
What is the variable for K?
What are the units
I'll show you in a second. Okay.
K divided by X minus N times Celsius.
Yeah. What he said.
I'm just really smart.
Yeah. All right, can I move on to the next slide? So what I'm going to do is I'm going to open up another presentation. And we're going to do an example problem real quick. Man, we are pushing my computer to its limits here, which is hilarious to me. Like, this thing is really struggling. All right, so this one says the styrofoam ice box is has a total area of 0.95 meters per second squared. That's the area of it. The walls have an average thickness of 2.5 centimeters, and the ice box contains water and ice and a canned beverage. The temperature on average is about 0 degrees Celsius. That's, you know, because of the ice. And then the inside the box is kept cold by melting the ice. How much ice melts in one day if the ice box is kept in the trunk of a car, and the trunk of the car is 35 degrees Celsius. So what I'm going to do real quick is, before we begin this, in the textbook online, there's this table. I'm not going to make you guys write it down, but it's basically thermal conductivity. They measure that, and these are averages. So silver has a thermal conductivity. Its K value is 420, copper is 390, gold is 318. And if you go down here to the bottom, things like wool, which keeps you warm. The reason it keeps you warm is it keeps the heat that your body naturally produces inside. So that's 0.04, so it's a very small conductivity. Styrofoam, as you can see, is very small as well. It's probably the least conductive material on the list, aside from like wood and stuff like that. Asbestos, they don't use that anymore, but they used to use that as insulation. It's not safe, I guess. So they don't use that anymore. Okay, so anyways, those are the values for K, and we'll plug some values in here in a second. So the way that we approach this problem is we're definitely going to use that formula we just wrote down. So we're going to say that QT is equal to the thermal conductivity times the area times the difference in temperatures. You have temp 1 and temp 2. One of them is going to be higher than the other because that's how these problems are set up. We're talking about heat transfers, right? And this is for conduction, right? So today we're just focusing on conduction. Okay. Now heat is used to melt the ice. So just a little bit of a heat used to melt the ice. And let's write this over here. Melt ice. And I don't know if you guys remember this from your homework a couple sections ago. We would have the mass of the ice times the latent heat for freezing, right? Okay, so that's going to be kind of critical. And then also, so basically we know the values. So let's list some of the things that we know and the things that we don't know. So I know that the area is equal to, and because it's in meters cubed, remember we want everything to be in the meters, and so area should be meters cubed. Our thickness or distance is 2.5 centimeters, but we need to convert that to meters, so that should be 0.025 meters, right? Temperature, the lower temperature, and it doesn't necessarily have to be this way, but that's generally how it works. I can't think of a situation where, in general, T2 is greater than T1. In fact, we wrote that down. T2 is 35 because heat flows from a higher thermal energy to a lower thermal energy. And so that's usually how you do that. And then I'm thinking if there's anything else. Oh, also, our time has to be in seconds. Okay. And we said 1 day. So 1 day, right? We got to convert that to seconds. So remember, there in 1 day, there are 24 hours.
Can we just do 3,600 instead of doing 2 times 60s?
What are you talking? Yeah, that's what I'm going to do. And so then remember that 1 hour is 3,600. So essentially, your time is 86,400 seconds. All right, woo, that's a lot of work. So then I know I can calculate Q, right? Because Q is the temperature that we need to melt the ice. So Q then becomes, so what I'm gonna do here is I'm gonna say Q over T is equal to, if we look up let me plug this in first, and then we'll circle back to melting the ice. So QT is equal to the thermal conductivity of styrofoam, and if you pull that up in that table, it's 0.011 or 0.010, sorry, and I'm going to skip the units because I'm running out of space, times 0.95, right? That's the area they gave us, and then the difference in temperature, so this would be 35 minus 0 all over the thickness, and remember the thickness has to be in meters, or no. Yes, because I'm just double checking. Now, so what that means, and this is what threw me off for a second. Remember, Q is a measurement of heat, and then T is time. So we're doing heat energy over time. So yeah, it's joules per second, which is what, technically?
Joules per second.
No, joules per second is what? Watts. So anyways, so when I crank through all this math, right, I end up with this value is 13.3 joules per second. Sorry, I didn't write all the units out so you can see it cancel. But now I have that value, right, joules per second, which is a measurement of energy. And so if I want to find the actual energy, right, so if I want to find Q, Q is technically equal to Q over T times T, isn't it? Oh, shoot. I hate when my thing does that. Right? Because the T's technically cancel. So what does that mean? Well, I know that QT is this value. So I'm going to say 13.3 joules per second times the time. What's the time? 86,400 seconds. My seconds cancel. And so then my actual rate of heat, or my actual energy, is going to be this 13.3 times 86,400, which is about 1.15 times 10. Oh, this is frustrating. Times 10 to the 6 if you plug that in a calculator, and that's joules. Right? Now we're not quite done. So we had to do all of that to find the heat energy, right? And this is technically the heat energy used over the course of a day, right? So then when they say how much ice is melted, what they're really referring to is the mass. So we're going to bounce back to this little formula up here, right? And we know that the heat energy is equal to the mass of the water times the latent heat of water for freezing. And so if I want to find the mass, I'm simply going to divide by the latent heat for freezing. These cancel. And I get the mass is equal to Q over the latent heat for freezing for water. Or 1.15 times 10 to the 6 all over. And if you don't remember this is in one of those tables. If you go back a couple sections, 334 times 10 to the 3rd. And this is in joules. This is joules per kilograms. The joules cancel, and then the kilograms get tossed up to the top. So then the mass is just 3.44 kilograms. So that's how much ice melts. And then, you know, the relationship, 1 kilogram of water equals how much water? 1 liter. So it's 3.44 liters. They don't ask you that. If you wanted to convert that to pounds, you just multiply that by 2.2, right? Okay. So anyways, what they're saying is that bags of ice are sold in a pound. The big bag is 7 pounds. So in the textbook it says if you would need at least 1 big bag, or not, the small bag is 7 pounds, the big bag is 22. So they would say you'd use up about 1 bag of ice per day to do this, to keep the cooler cool. Okay. So then I'm going to do another problem while I got this up. Did you guys have that all written down?
Yeah.
Do you have any questions on that one? Okay. So let's do one more problem while I have all this stuff up. So this is another one that so if you have water boiling in an aluminum pan on an electric element stovetop, the saucepan has a bottom that touches the element, right? And then the diameter of the pan is 14 centimeters. The boiling water is evaporating at a rate of 1 gram per second. What's the temperature difference through the bottom of the pan? In other words, how much energy is being transferred through the bottom of the pan to the top where the water is boiling? So if I take, this one's going to take a little bit of time. So we have the same relationship where I say Q over T lowercase t, which is time, heat over time, is equal to conductivity times the area, right, times the difference in time, or temperature, sorry, all over D. And what they want to know is the temperature difference. So I have to take this equation and isolate this. Nothing up my sleeve. You guys ready for this? I'm going to multiply both sides by D. So now I have dq t is equal to Ka and then T2 minus T1. That's not that hard. Then I'm just simply going to divide by Ka, and then over here I'm going to divide by Ka. And I'm going to keep these separate. So over here I'm going to write this as Q over T times D over Ka. So heat over time times the distance over thermal conductivity times the area is equal to the temperature difference. Easy peasy, right? Okay, well, what do we know? Well, we know that the thickness of the pan, in this particular case, is 0.8 centimeters, but we have to convert that to meters. So if you use your big brains, we get 8 times 10 to the third meters. That's the thickness. The area is a circle, right? So the area of a circle is pi times the radius squared, but they don't give us the radius. They tell us the diameter. The diameter is 14. The radius is half of that, so it's 7. So I get pi r, which is 7 squared, right? And if you, I don't know, if you do that on, and it's not 7, it's 0.07, I think. Something like that. Anyways, when you get all that math, when you crank through that math, you're going to get 1.54 times 10 to the negative 2. And that is in meters cubed, because I converted stuff.
You mean meters squared, not meters cubed?
Yeah, meters cubed. Yeah, you know what I'm saying. And then I need the thermal conductivity. And so, what do I need the thermal conductivity of, guys? Yeah. So, just so you believe me, nothing up my sleeve, the thermal conductivity of aluminum is 220. Okay? So we're gonna go with that. And this is a weird one. This is joules per second meters. Or no, I think the meters is up on top. Hold on.
No, it's all on the bottom. Yeah.
You sure?
And then it's times degrees Celsius.
Is it degrees Celsius on the bottom?
Yeah, it's all on the bottom.
Okay. Then we're going to calculate the heat. Now for this one, remember that Q is equal to the mass, right, times the latent heat for evaporation. Well, they told us the mass. Did I write the mass down? While we're calculating, so this is funny. So the rate is, So the evaporating rate is the heat transfer rate. So we're doing 1 gram per second, right? So QT would be, so our assumption is, what is 1 gram? So we're going to separate that. We're just going to focus on Q. So this right here is QT, if you want to think about it, or that's what we're going to work towards. So we're going to solve for Q, and then we'll double back. So 1 gram, right? And then we need to convert 1 gram to kilograms for the formula to work. So our mass then would be 1 times 10 to the negative 3. That's a 3 there. I write too fast. The computer can't keep up. All right, and that's going to be in kilograms. And then I just need the latent heat for, you guys got that memorized off the top of your head? For vaporization for water.
2256.
Yep, 2256, very good. Times 10 to the 3. And I'm starting to run out of, but it's joules per kilograms. Okay.
So it just becomes 10 to the third.
Yeah, because the 10 to the third, the 10 to the thirds cancel, right? This cancels with this, and so you're just left with 2,256 joules. That's the heat energy, right? And then remember, this is the heat energy per second. So for QT, I'm just going to put that over per second. So I could say that QT is just going to be this per 1 second, or 2.26 kilowatts, right? Kilowatts, because joules per second is watts. You guys don't remember that maybe. I did teach it to you last May.
Well,
I don't know if you guys remember that.
it's been on our last, remember how Nolan assignment last.
Have it? Has it? All right. By the way, have we answered the question?
No.
No. But we've got a lot of information. So I've got QT now. Remember, what I'm trying to do is I'm trying to get the information so I can plug it in, and that'll give me my temperature difference. And right now we just have this. But we do know the thickness. We know the thermal conductivity of the aluminum, and we can calculate the area. We've calculated those things. So now, if I want to find the temperature difference, okay, and I'm just going to rearrange the temperature difference, T2 minus T1, is equal to QT times D over the thermal conductivity times the area. And now we have some numbers. I have this number over here, but I don't know why I converted it to kilowatts. Well, actually, the book did. I need to leave that in joules and then per second, because I've got some cancellations. This will be times the thickness, which would be 8 times 10 to the negative 3 meters, all over, this is the weird one, 220 joules per second meters degrees Celsius. And then that's going to be multiplied by 1.54, which is the area which we calculated. 1.54 times 10 to the negative 2 meters squared. Okay? Easy peasy. So if you plug all of that in the calculator, you get 5.33 degrees Celsius. That's the temperature difference. Now, do we know what the temperature is at the bottom of the pan? No. Could we kind of guess what the temperature of the boiling water would be close to? We could guess a minimum, right? It'd be at least 100 degrees Celsius. but we don't know. And so what we're really calculating is what is the temperature difference from the bottom of the pan to the top of the pan. Does that make sense? Okay. All right. Woo. I just found out that the Cybertruck in the temperature outside, that the air conditioning kicks on to keep it cool on the inside. Because my battery was...
Pardon the interruption. May the owner of the black Honda Civic with Notre Dame license plate parked in the bus lane please move their vehicle. Again, owner of the black Honda Civic with Notre Dame plate